A telescope the size of a tennis court, floating 1.5 million kilometers from Earth, just looked at a patch of the night sky roughly equal to 3 full moons held up against the darkness. It stared into that patch for a total of 255 hours across multiple observation sessions, and returned data that contained the positions, shapes, distances, and physical properties of nearly 800,000 galaxies. Not 800,000 stars, 800,000 entire galaxies, each one containing hundreds of billions of stars of their own, and that was in a region of sky so small that you could cover it completely with your outstretched hand. That result, published in June 2025 by the International Cosmos Web Collaboration, and then extended into the most detailed map of cosmic structure ever produced in May 2026, did not simply add numbers to a catalog. It demolished a version of the universe that humanity had been carrying in its head for decades, and replaced it with something vastly more populated, vastly more complex, and vastly more difficult to emotionally absorb than anything our best instruments had previously shown us. The James Webb Space Telescope did not build a bigger universe. It revealed the universe that was already there in full, waiting behind a wall of light that our previous instruments lacked the capability to translate. To understand why the 800,000 galaxy number is so shocking, you have to understand what was previously known about the same region of space. The famous Hubble Ultra Deep Field image, released by NASA in 2004 and celebrated for years as the deepest and most comprehensive view of the distant cosmos ever captured, revealed approximately 10,000 galaxies in a patch of sky roughly the size of a grain of sand held at arm's length. That image was considered an extraordinary scientific achievement. It was studied for years. It became one of the most reproduced scientific images in history. And it was profoundly, systematically incomplete in a way that nobody could fully appreciate, until Webb looked at comparable regions with different instruments. When UC Santa Barbara physicist Caitlin Casey, who co-leads the Cosmos Webb project, described the difference in scale between the Hubble image and what Cosmos Webb produced, she put it this way: if you printed the Hubble Ultra Deep Field on a standard piece of paper, the Cosmos Webb image at the same depth would need to be a mural 13 feet wide and 13 feet tall. And the Cosmos Webb image is not just bigger, it is 10 times denser with detected structure than the previous generation of surveys predicted it should be at equivalent depth. 10 times more galaxies than expected. Not 10%. 10 times. That correction is not a refinement. That is the collapse of a framework. The reason those galaxies were hidden is not mysterious once you understand the physics, but the implications of that physics run very deep. Light from ancient and distant galaxies does not arrive looking the same way it left its source. The universe has been expanding continuously since the Big Bang, and as space stretches, the light traveling through it gets stretched along with it. This process shifts light toward longer and longer wavelengths as it travels. Visible light, the light the human eye can detect, and that ordinary optical telescopes are built to capture, gets pulled progressively toward infrared wavelengths by this stretching. Infrared light is heat radiation invisible to human eyes, and until Webb, essentially invisible to the best space telescopes humanity had built. The Hubble Space Telescope was optimized for visible and near ultraviolet light. It could see some near-infrared wavelengths, but not the deep infrared bands, where the most ancient and distant galaxies have had their light shifted by billions of years of cosmic expansion. Those galaxies were not absent from the data because they did not exist. They were absent because the instruments could not hear the frequency they were broadcasting on. Webb was designed from the ground up to hear exactly that frequency. Its 18 gold-coated beryllium mirror segments, spanning 6.5 meters across, collect more than 6 times as much light as Hubble. Its infrared instruments are sensitive to wavelengths that Hubble could not reach. When those instruments were pointed at regions that previous surveys had found relatively sparse, the darkness overflowed with structure that had been there all along, completely invisible, patiently waiting for a telescope capable of seeing it. This is the core of what makes the Cosmos Webb result philosophically significant beyond its scientific content. The universe was not misunderstood because data was wrong. It was misunderstood because the instruments looking at it were capturing only a thin, visible slice of reality. Every image ever taken before Webb, every deep field survey, every galaxy catalog, every cosmological simulation calibrated to observational data, was built on a picture of the universe that was missing the majority of its early population. Researchers at UCR, who published the most detailed cosmic Webb map in May 2026, described the jump in depth and resolution from Hubble to Webb as truly significant, and noted that the cosmic Webb, the vast invisible skeleton of dark matter filaments and sheets that connects galaxies across all of space, can now be traced with clarity all the way back to when the universe was only a few 100 million years old. That era was essentially out of reach before JWST. The cosmic web that astronomers had been modeling for decades based on what Hubble could show them was a smoothed-over approximation of a far more complex and detailed reality. Webb is not showing us a corrected version of the old picture. It is showing us the actual picture for the first time, But the population of hidden galaxies is only the first of the revelations that make Webb's accumulated findings so genuinely unsettling. Because alongside the sheer number of previously invisible galaxies, Webb has been systematically delivering a second discovery that is harder to explain and has been generating increasingly urgent scientific debate since its first results emerged. The galaxies Webb has been finding in the earliest periods of cosmic history, from the first 300 million to the first billion years after the Big Bang, look nothing like what the accepted model of galaxy formation predicts they should look like at that age. The accepted model, called lambda CDM, describes a universe that starts from nearly uniform hydrogen and helium gas and builds structures slowly and progressively through gravity. Gas collapses into stars. Stars form into small, irregular galaxies. Small galaxies grow gradually through billions of years of mergers and gas accretion into the large, structured spiral and elliptical galaxies seen in the modern universe. This model makes specific quantitative predictions about the mass, brightness, and structural complexity of galaxies at each stage of cosmic history. Webb keeps finding galaxies that violate those predictions. In the summer of 2025, Webb confirmed a galaxy cataloged as JWST at a redshift placing it just 300 million years after the Big Bang. This galaxy is not a small, dim, irregular smudge of early star formation. It is spatially resolved, meaning it has measurable physical size and structure. It is extremely luminous in ultraviolet light, meaning it contains large numbers of massive energetic stars. And its spectroscopic signature reveals the presence of heavier chemical elements, including oxygen, that can only be produced inside stars through nuclear fusion and then scattered into the surrounding environment when those stars die. For a galaxy to contain those elements 300 million years after the Big Bang, entire generations of stars must have already been born, burned through their fuel, and exploded before that point, distributing their material back into the gas clouds that form the next generation. The timeline implied by what Webb observed in JWST is tighter than the lambda CDM model comfortably accommodates. Then, in January 2026, astronomers at Texas A&M University reported a Webb observation of at least 5 galaxies in active collision with each other just 800 million years after the Big Bang, distributing heavy chemical elements beyond their own boundaries through the violence of the merger. Galaxy mergers at that level of organization and frequency so early in cosmic history were not predicted to be typical in the standard model's framework. These findings have not broken cosmology, and that distinction matters. No peer-reviewed consensus has formed around the claim that the standard model is wrong. What has formed is a growing body of evidence that the standard model's predictions about the early universe need either significant revision or entirely new physics to accommodate what Webb is actually observing. Some astrophysicists propose that star formation in the early universe was dramatically more efficient than the models predict, converting available gas into stars at rates far higher than the standard model assumes. Others point to possible roles for dark matter behavior in the early universe that current models do not capture accurately. A smaller group argues that the findings hint at something genuinely new at the level of fundamental cosmology. The scientific community is working through these possibilities methodically, and Webb is generating new data to test them every month. But the central fact is established. The early universe looks nothing like what we predicted it would look like before we could actually see it at this resolution. The theory that was built on incomplete observations needs to grow to fit observations that are no longer incomplete. And then there is the largest dimension of what Webb has confirmed, the one that requires sitting within silence for a moment before it lands properly. The universe that Webb is revealing as densely populated and as structurally complex as it turns out to be is not the whole universe. It is not even the majority of the universe. It is the fraction of the universe from which light has had enough time to reach us since the Big Bang. The observable universe is the specific sphere of space centered on Earth, from which ancient light traveling since the earliest moments of cosmic history at the fixed speed of 300,000 kilometers per second has managed to bridge the distance to our instruments across 8 billion years of travel time. That boundary is called the cosmological horizon, or the photon horizon, and it sits at approximately 46.5 billion light years in every direction from Earth. That number is larger than the age of the universe in years would suggest, because space itself has been expanding the entire time light was traveling through it, carrying the sources of that light much farther away than the travel time alone would place them. The galaxy JWST, whose light traveled for 2 billion years to reach Webb, is now estimated to be approximately 33. 8 billion light years from Earth, carried there by the expansion of space that began before its ancient light, had even reached the halfway point of its journey to us. The cosmological horizon is a boundary of observation, not a boundary of existence. The universe does not end at 46 billion light years. That is simply the edge of what we can see. Beyond it, the universe almost certainly continues, How far it continues is a question cosmology cannot currently answer from within its own observational limits. Inflation, the period of extraordinarily rapid expansion in the first fractions of a second after the Big Bang, would have stretched space to dimensions far larger than our observable bubble. Regardless of whatever the local geometry suggests, some cosmological frameworks suggest the true universe is hundreds of times larger than the observable portion. Others suggest it is effectively without boundary. The honest answer is that the observable universe is our prison of perception, not a map of all that exists, and nothing Webb can observe will ever change that fundamental epistemic situation, because it is built into the physics of light speed and the geometry of cosmic expansion. But here's the dimension of this that is genuinely difficult to absorb emotionally. The observable universe is not static. It is shrinking in terms of what it contains, because dark energy is accelerating the expansion of space. Dark energy, confirmed again by independent measurements published in June 2026 using corrected supernova data, constitutes approximately 68% of the total energy content of the universe and is driving space to expand at an increasing rate. As a result of that acceleration, distant galaxies that are currently observable are being carried away from us at ever-increasing velocities. Some of the galaxies Webb observes are already receding from Earth, faster than light can travel, which means any signal they send today will never reach us. They are observable only because the light currently arriving from them left them billions of years ago when the expanding space between them and us had not yet grown fast enough to prevent their ancient photons from making the crossing. But those ancient photons already in transit for billions of years will be the last ones we ever receive from those galaxies. The light they are emitting today is being carried away by expansion faster than it can travel toward us, and it will never arrive. A science journalism piece published in late July 2026 captured this trajectory with precise language. The accelerating expansion driven by dark energy will eventually push nearly every galaxy beyond our local group out of our observable reach forever, until the universe appears almost empty to any future observers. The cosmological event horizon, the boundary beyond which nothing can ever reach us again, will eventually stabilize at approximately 60 billion light years. But by then, the vast majority of what we currently observe will have crossed beyond it permanently. A civilization studying astronomy in the very distant future, tens or hundreds of billions of years from now, will look outward and see a much smaller, apparently isolated universe. The cosmic microwave background radiation, the faint afterglow of the Big Bang that current instruments detect as a uniform glow of ancient heat radiation, will have redshifted to energies below any conceivable detection threshold. The large-scale structure of galaxy filaments that Webb is now mapping in unprecedented clarity will be invisible, its constituent galaxies carried far beyond the horizon. The future civilization will have no observational evidence of the Big Bang, no visible galactic web, no way to determine from the sky above them how enormous the cosmos actually is. They will live in a cosmically isolated remnant of a much richer observational universe with no way of knowing what they have lost access to. Which is why what Webb is doing right now in this specific era of cosmic history carries an urgency that no human engineering challenge has ever quite matched. We are living in a cosmically privileged moment of visibility. The universe is structured enough, bright enough, and accessible enough that a sufficiently capable telescope can read back nearly its entire history. Webb is that telescope. The Cosmos Webb data is available to any researcher in the world. The catalog of nearly 800,000 galaxies spanning almost all of cosmic time is publicly released. The Cosmic Web Map tracing the largest structures in the universe back to its first billion years is published and documented. The impossible galaxies of the early universe are cataloged and under active scientific investigation. What Webb is accumulating is not just data for astronomers. It is the most comprehensive reading of the cosmic record that any intelligence has ever attempted during one of the last eras in which so much of that record is still visible at all. The universe will not always be this legible. The window is open now, and Webb, floating in its precise gravitational balance, 1.5 million kilometers from Earth, is reading everything it can reach before the expansion of space carries any more of it beyond the edge of what light can ever bridge. What comes after the observable horizon? What fills the universe beyond the last light that will ever reach us? What the total scale of everything that exists actually amounts to? These are questions that no instrument will ever answer from within our cosmic bubble. The universe is not just bigger than we thought. It is bigger than observation can ever confirm. Webb has shown us the true scale of the part we can reach, and in doing so, it has forced us to confront the scale of what we will never reach, the light that will never arrive, the structures we will never map, and the civilizations that may be living in the dark beyond the edge of our visible bubble, unaware that somewhere across the cosmic void, another civilization once looked up with a telescope the size of a tennis court and glimpsed the true scale of everything, just before the darkness swallowed the rest.